Okay, here is the first of our lessons on rotational dynamics. And I'm going to give you a quick little revision lesson on how the circular motion, on the theory on circular motion first, and then we'll move from there. So let's imagine we have our object moving around in a circle from a center point. It's at radius r from that center point, and it's moving around the circle at omega. Okay, let's remind ourselves what that means. Omega, first of all, this is the term which represents how many angles this, let's say this axle is moving through in a given number of seconds. So omega is the number of angles the arm is moving through. Per second. So in a straightforward way, theta over t. However, we might like to talk about it in terms of how, well, it makes life easier if we talk about this in terms of radians. So we think about how many radians it's going through per second, hence the unit, radians per second. And also, it's much easier to think of a time period, the time it takes for one complete revolution. So therefore, the number of radians in one complete revolution are 2 pi, and the time period it takes to go around is given as t. So omega is 2 pi over t. Now this means that all points along this arm are moving around at the same number of, the same angular speed. However, the actual speed, the linear speed at any point, is going to be different depending on where you are on the arm. The closer you are to the hub, let's imagine this is a wheel, the closer you are to the hub, the smaller the angular speed, and the further you go out, the greater the speed until you get to the maximum speed, which is right on the end of the arm. Though the angular speed of all of these is the same, you still have the same number of omegas. So therefore we can talk about, we relate our angular speed to our real speed in the sense of velocity, v, is omega times by the radius. Angular speed, speed as you understand it, and r is the radius at whichever point you are away from it. So really we're looking at the velocity of the endpoint because we're multiplied by the maximum distance r. Okay, hopefully that's a recap of what we dealt with before in circular motion. So here's an example, for instance. Let's use a geostationary satellite. I'm going to give you the radius. The radius from the center of the Earth is approximately 4.2 times 10 to the 7 meters. And I want to know what's the angular speed of the geostationary satellite, and then what's the real speed at that distance. So if you think you know how to work it out, hit pause. Otherwise, here comes the answer. Okay, omega is going to be total number of one complete turn divided by the time period. And because it's geostationary, we know that it takes the same time period to go around the Earth as the Earth takes itself to go around its own axis, which is 24 hours. So our time period is 24 hours, and of course we need to convert that into seconds, because this is the number of radians per second. So we have this value, which gives us 7.3 times 10 to the minus 5 rads per second. And therefore our velocity at that point is going to be simply omega r, which is 7.3 10 to the minus 5 by 4.2 10 to the 7 meters, which gives us something equivalent to 3,054 meters per second. Pretty fast. Good, okay. One other thing, which we probably didn't really touch on too much when we did circular motion, but that's the idea that rather than talking about the number of radians per second, people might talk about RPMs, or revs per minute. Or even, we might talk about the number of hertz. which is the number per second. So how do we easily convert these two units, which we might be given in any problem, into omegas? Okay, very simply, let's talk about, let's have an example. Let's say something was given 16 RPMs or 16 Hertz. How do we convert that into omega? Well, 16 RPMs, let's go for that to start with. 16 revs per minute means 16 revolutions, and if each revolution was 2 pi, because obviously we're talking about complete revolutions, and we're having that occur in 60 seconds, because 60 seconds equals 1 minute. So therefore, it's a very easy conversion. That is 16, or your RPMs, multiplied by 2 pi over 60. Bear that in mind. Actually, that gives us 1.68 rads per second. Okay, what about if we want to convert into the hertz? Well, this time, hertz implies if you're 16 hertz, you're talking about 16 rotations per second. Because it's in seconds, that makes the sum a lot easier. So if it's in hertz, if it's RPMs, you multiply by 2 pi over 60. In hertz, you multiply by 2 pi, which gives us something like 101 rads per second. Okay then, so a quick recap of where we were at the end of circular motion topic. Now, let's turn to the rotational dynamics for real here. Now, what I'm going to do is start off with the idea that everything we did in AS in Unit 2, I think it was, with SUVAT equations, dealt with straight lines. And we either had non-accelerating frames of reference, i.e. what I like to call GCSE, in which simply the displacement is equal to the velocity multiplied by the time. Really straightforward. So therefore, if an object were moving at a velocity of so many meters per second, that meant that every second this object was covering that number of meters, the number of meters represented by the velocity. And if you now imagine we take that point and we wrap this up, then very simply we can see an analogy between, I hope, the displacement, that's occurred, and that being represented as the number of angles which you're going around. Theta, as it were. I don't know why I've drawn that twice. Anyway. And of course, in order to work out the number of angles which you've gone around this time, it's the angular velocity multiplied by the time period which it's rotating. So you can see the analogy between the displacement and the angles and the angular speed and the real speed that we're familiar with. Okay, straightforward. However, if we were in accelerating frames of reference, which is our AS knowledge, this is where we start to get to AS, then you know that it's not as easy just to write S is V times T. We need the SUVAT equations. Displacement, initial speed, final speed, acceleration, time. And we have three major equations which help this. V is U plus AT, S is UT plus a half AT squared, and finally V squared is U squared plus 2S. Those are the major ones I use. I know you could have some variations in those. However, those are the major ones. Now, because you have this analogy between displacement and angles, then there is no reason why you can't have all of these as rotational mechanical kinematic equations. If we replace everything with theta for S, initial angular speed, final angular speed, acceleration is a new term called alpha, which I'm going to come on to, and time is still time. And suddenly all of these equations will be reconverted into rotational mechanical equations, which are final angular speed is initial angular speed plus alpha t, angular acceleration. We're going to come on to that in a minute. Number of angles you've travelled through is initial angular speed times time plus a half. Alpha angular acceleration t squared, and final angular speed squared is initial angular speed squared plus 2 alpha theta. Okay, so hopefully any situation you see of a rotational object going around, you could almost cut it, reel it out, and see how that equation, how a linear equation might apply, and they are identical. So let's just define quickly what alpha is, and then we'll move on and give some examples. Okay, if acceleration defines the speed increase or decrease per second, or the change in speed per second, then alpha surely defines the change in angular speed per second. Where alpha acceleration is v minus u over t, alpha is omega final minus omega initial over t. And the link between the two is that the real acceleration, or linear acceleration, is alpha r, just like before. And of course, alpha is going to be measuring radians per second squared. Good. Now, let's try some examples. And hopefully all makes sense. I'm going to leave those kinematics up there. And hopefully we'll be able to use them neatly. There's 2 examples coming up. Okay, first one. We have a wheel. Let's say radius 1.5 meters. And it starts from rest. And it reaches 20 RPMs in 1 minute. Okay. What is alpha? And what is the acceleration at the rim of the wheel? And finally, no, let's start with that. Okay, if you think you know, hit pause. Otherwise, here comes the answer. Okay, so alpha is very simply, we need to work out the change in omega divided by the change in time. Omega is going to be 20 RPMs, and if you remember, to change from RPM into radians, you 2 pi over 60. And that gives us a figure of about 2 over 3 pi. I don't like leaving it in pi, but I'll just leave it in there until we get to the next calculation. Okay, so alpha therefore is 2 over 3 pi divided by the 1 minute, which is the 60 seconds. And once we put those together, we come up with 0.035 radians per second squared. Okay, what's the real acceleration then at this point there? Well, real acceleration is going to be alpha times by the radius, which is simply 0.035, multiplied by the radius of 1.5, which gives us 0.05 meters per second squared. Okay, good. Now, the next question is, how many turns? Or should I say, and angles, radians, sorry, has it made in that time? We're going to employ another SUVAT equation here. How many turns has it undergone? Well, in this time, well, if you think you know, hit pause, otherwise here comes the answer. Let's use this SUVAT. So, theta is omega I t plus half alpha t squared. Of course, initially it was at 0, so that leaves us just with a simple half alpha t squared, which gives us half by 0.05 by the time period we're talking about here is we're running over 1 minute. So that's 60 squared. And that gives us a grand total of, so I haven't worked this one out. Oh yes, I have that. 63 radians. If I wanted to work out the number of turns that is, of course, then I go for 63 divided by the number of radians in one turn, which gives me 10 turns. Excellent. So you can start to see how there is this analogy between linear accelerated motion and rotational accelerated motion are the same, so long as you change distance, angles, initial and final for angular speeds, accelerations for alphas, but t remains the same, interestingly. 2 more examples and then we're done. Let's go for the next one. Let's say we have an object. We have an object that uniformly accelerates, rotation accelerates, from initially at 0 to a final angular speed of 500 rads per second in 10 seconds. Then it continues at 500 rads per second for 50 seconds. I think this is actually a centrifuge calculation. Okay, first of all, what is the angular acceleration in the first 10 seconds? And then how many radians has it turned through? Okay, you think you know, hit pause, otherwise here comes the answer. Okay, alpha to start with is very simple. The change in angular speed divided by the time taken. It's obviously started, it's gone to 500, it started at 0, that's happened in 10 seconds, giving us very simply 50 rads per second squared. Okay, theta, well, just as before, we use one of our kinematic equations, rotationally, to give us how far it's gone through whilst accelerating. It started from 0 speed, so that gives us a simple half by the 50 by the 10 seconds squared, which gives us a grand total of 2,500 rads. So this is whilst it was accelerating. The first 10 seconds are whilst it's accelerating. I'll call that x. Whereas theta non-accelerating gives us much simpler omega t. And you know that it's travelling at 500 radians per second, multiplied for the 50 seconds remaining gives us 2,500 rads. Add the two together, gives us 27500 radians, totally over this 1 minute, which is approximately the same as 4,300 and 80 turns. Okay, last example. Let's imagine we have a car engine. It ticks over at 2000 RPM. It takes 20 seconds to reach that angular speed. Then carries on for 2 minutes. Okay, same as before. First of all, well, let's go for, yes, simply, how many turns is it undergo? How many turns? How many radians? Stroke turns has it undergone? Think you know, hit pause, otherwise here comes the answer. Okay, first of all, what is omega? Well, 2000 RPMs gives you 2000 260 radians per second, that's 209 radians per second. The acceleration is the change in omega over the change in time. It started from 0, so therefore you know the change is 209, divided by the 20 seconds gives us 10.5 radians per second squared. You can see that. Okay, so the accelerating theta is omega it plus a half alpha t squared. Obviously that goes to 0, giving us a half alpha t squared, which is a half by 10.5 by 20 squared. So car goes to, and it's in 20 squared seconds. Let's try that then. So just need to tap this into the calculator. $2,100 radians. Okay then, theta non-accelerating gives us omega by the time remaining, and that gives us omega's running at 209 radians per second, multiplied by the 2 minutes minus the 20 seconds. So that's 209,000 rads. And add these two together gives us finally 23,000, if you can see that, radians. Good, hope that's all made sense. Next time we'll move on to ideas.